Today we're going to continue looking at section 6.2. We're going to use the sum and difference formulas for cosines and sines again, and now we're also going to be looking at sum and difference formulas for tangents. So we spent yesterday looking at if I gave you the cosine of an angle that wasn't a part of a unit circle, how we could find two numbers that either add or subtract to get you the angle that was given, and we could go ahead and plug that into our formula. Well, as you can see, this is a little bit different from what I gave you yesterday, because here we have essentially the sum or difference formulas already filled out for us. So just a quick reminder, remember these were the four formulas that we've been talking about. And so with the first one being that the cosine of 70 degrees times the cosine of 40 plus the sine of 70 times the sine of 40, hopefully we recognize that that fits the pattern of the second formula here, where it's really the cosine of alpha minus beta. So what I'm going to do is I'm going to condense this down. This is a cosine formula, and our two angles were 70 and 40. And once again, when we have cosine, we always are, whatever the formula is, we are doing the opposite sign with those angles. Notice that 70 minus 40 is a 30-degree angle. And 30 degrees is an angle that we have on our unit circle and something that we can very easily sketch to figure out what that ratio is. So if you need to sketch a picture, don't forget that 30 degrees is in the first quadrant. And that's across from the smallest side. Everything is going to be positive in the first quadrant. And so if I'm thinking about SOHCAHTOA, we know that cosine is adjacent over hypotenuse, so this becomes the square root of 3 over 2, and that'd be my answer. If we take a look at this next one, the sine of 60 times the cosine of 30 minus the cosine of 60 times the sine of 30, well, because we're dealing with sine, cosine, cosine, sine, hopefully that recognizes the fact that it's going to be one of our sine formulas. So I know that this is going to condense down into the sine. Now, because we are subtracting, that is going to fit the formula where alpha and beta are subtracting. So 60 would be the alpha minus 30, which is the beta. Notice that if I actually subtract, 60 minus 30 is going to be 30 degrees. And so I already technically have the picture sketched from problem number 1. We can very easily find what the sine of 30 degrees is. Sine is opposite over hypotenuse, so that gives us 1/2. All right, so these cases, I already had it spelled out for you. We were thinking about condensing it down to a single sine or cosine, and then being able to evaluate from there. Now we can take our different sum and difference formulas and apply them into verifying identities. So remember, to verify identity means that you focus on only one side and manipulate it to look like the other. Hopefully we're okay with noticing that, we've got cosine being subtracted in the numerator, and then we have a fraction on the left side that might be a little bit more complicated. So I'm going to start with the left side. And so then our goal is to turn it into the right side. So to start manipulating, I'm going to focus on the fact that the numerator is the difference of cosines. Well, that's this formula right here. So I'm going to rewrite this as cosine of alpha times cosine of beta plus sine of alpha times sine of beta. And that's still all over cosine of alpha times cosine of beta. Okay, notice that I want to turn it into two separate terms. That's what the right-hand side is. So when you have one fraction, but you want to turn it into two things, well, let's follow the strategy of splitting apart the fraction. I'm going to take the first part of my numerator and put it over my denominator, plus I'm going to take the second half of my numerator and put it over the same denominator. Notice that the first fraction is going to reduce down to 1, and our second fraction is sine on the top, cosine on the bottom. Well, sine over cosine, that's the quotient identity, and so that turns into then the tangent of alpha times the tangent of beta. So we then got what we wanted on the right-hand side. All right, here's our last example before we move on to the tangent. So it says, let's find the exact value for the sine of 5 pi over 12 using the fact that we can get that number by adding pi over 6 plus pi over 4. So thinking of this as alpha and beta. Okay, so we've always done everything in terms of degrees, but realized that we could still do things in terms of our radian values as well. So, So if I think of my sine, okay, so essentially this problem is the sine of pi over 6 plus pi over 4. And so thinking about our definition, we can split it up, if this was alpha and beta, as the sine of alpha times the cosine of beta. We keep the sign the same, so plus, and now I want the cosine of alpha times the sine of beta. All right, so we need to, if you don't use a unit circle, sketch a picture. Let's start with pi over 6. Remember, pi over 6 is really a 30-degree angle, and 30 degrees is in the first quadrant. So across from 30 is 1, we've got the square root of 3 and 2. So there's my pi over 6 or 30-degree angle. So that means I get to replace the sine of pi over 6. Sine is opposite over hypotenuse. I get to replace that with 1/2. Moving over to the other side, cosine then is adjacent over hypotenuse. So that's the square root of 3 over 2. I need to know what pi over 4 is. Well, remember pi over 4, let me put this down here, is a 45-degree angle. And so 45 is in the first quadrant. The two legs are the same. The hypotenuse is the square root of 2. So cosine of pi over 4 is adjacent over hypotenuse. So remember, 1 over the square root of 2. I'm going to rationalize that. Turns into the square root of 2 over 2. The sine of pi over 4, opposite over hypotenuse, is the same thing. It rationalizes into the square root of 2 over 2. Multiply fractions straight across. 1 times the square root of 2 is the square root of 2. That would be over 4. Plus square root of 3 times the square root of 2 is the square root of 6. Still all over 4. So that's why putting them together, this would be my final answer. All right, here are the two sum and difference formulas for tangents. Okay, so notice that when we are dealing with tangents, we have a fraction in order to create this formula. Whatever sign is in what they're doing, alpha plus beta, notice that that exact same sign is in the numerator. Down here, alpha minus beta, that sign is in the numerator. Notice that the opposite sign then is in the denominator. All right, so pause and write these down if you need to. And now let's take a look at a couple of examples. We're finding the exact value for each expression. Notice that tangent of pi over 6 plus pi over 4, so our alpha and our beta. Thinking about what we just talked about, here were our two different formulas. So when we are adding, we're using the top formula up here. So this is going to turn into the tangent of pi over 6 plus the tangent of pi over 4. And that would be all over then 1 minus the tangent of pi over 6 times the tangent of pi over 4. So just like we did with the last problem, we are going to have to figure out what pi over 6 and pi over 4 are, and then sketch that picture or use your unit circle to help us. So remember, pi over 6 is a 30-degree angle, so first quadrant. So 30 degrees, we got 1 across from it, square root of 3, and then 2. Remember, tangent is opposite over adjacent. So opposite in this case would be 1. Adjacent is the square root of 3. So I'm going to rationalize that, and tangent of pi over 6 is the square root of 3 over 3. Okay, so wherever I see the tangent of pi over 6, I'm replacing it with the square root of 3 over 3. All right, so now I want to do the same thing with pi over 4. Well, pi over 4 is a 45-degree angle, so that's in our first quadrant. The two legs are congruent. They're both 1. The hypotenuse is the square root of 2. Remember, tangent, once again, is opposite over adjacent, so 1 over 1 is just 1. So that's where tangent of pi over 4 gets replaced with the number 1. So if we are just then simplifying, we'll have the square root of 3 over 3 plus 1 on the top. And then on the bottom, we'll have 1 minus, if I multiply those two numbers together, it'll stay the square root of 3 over 3. I am not going to ask you or make you have to simplify this any further. This can then just be our final answer. All right, so if we look at the next one, once again, alpha is first, beta is second. Because we are subtracting, that follows the second formula. So I'm going to plug everything in. We'll have the tangent of 4 pi over 3 minus the tangent of pi over 4. That's all over 1 plus the tangent of 4 pi over 3 times the tangent of pi over 4. All right, well, we already know what pi over 4 is. That's a 45-degree angle. We already have that sketched out from the previous problem. So it's just a matter of sketching what 4 pi over 3 is. Now, if we think about our unit circle, remember pi over here, if I keep it as a denominator of 3, is 3 pi over 3. So that means 4 pi over 3 is a little bit bigger. That's going to fall then in the third quadrant right here. But because it has a denominator of 3, think of that as then a 60-degree reference angle. So across from the 60 would be the square root of 3. But remember, I moved down in the third quadrant, so it's negative. So that means across from the 30 is 1. But because we moved to the left, that is negative. Our hypotenuse is positive. So tangent being opposite over adjacent means that I'm going to have negative root 3 over negative 1. So that just turns into a positive square root of 3. Minus, I know that the tangent of pi over 4, once again, that's just 1. That's in my numerator. My denominator is 1 plus. We'll then have the square root of 3 for the tangent of pi over 3 times tangent of pi over 4 would be 1. So when we multiply the numbers in the denominator, notice that this ends up being my answer. And once again, I'm not going to ask you to simplify this any further. Even though there's radicals in my denominator, I'm okay with this for your answer. All right, so then here we want to find the exact value of the expression. So notice that they are giving us the formula, and we need to work backwards to figure out, okay, notice that the two numbers in this are 405 and 90. Well, that means that that's alpha and beta, but what are we doing? Are we adding or are we subtracting when we're thinking about condensing it down to a single term? Well, looking at the formulas, once again, because subtraction is in the numerator, notice that that follows that second formula where tangent is really being subtracted. So this is going to condense down into the tangent of 405 degrees minus 90 degrees. So if we were to subtract those two numbers, that gives us 315 degrees. Now I want to evaluate. So 315, if we're thinking about where that is in our unit circle, remember 270 degrees is here, full circle is 360, so 315 falls in the fourth quadrant. All right, if we're thinking about a reference angle, that would end up being 45. Because we're in the fourth quadrant, not every side is positive. This side will be positive because we moved to the right. However, this leg is moving down, so it's negative. Hypotenuse is always positive. Well, remember, tangent is opposite over adjacent. So it's the two legs, since one is positive and one is negative. Negative 1 divided by 1 gives us -1 for our answer. So that's us using the sum and difference formulas for sines and cosines again, as well as now using sum and difference formulas for tangents. This is what I'd like you to try for homework on page 605. Do problems 22 through 36 even.